Okay, so the two objectives today for power, we're going to talk about how power is related to energy conversion rates and calculate power and its cost. Yeah, we're recording today. I know, 19.2 didn't record, but I'm going to record with the other class today. We're going to do that lesson. So let's take a look at our theory for power and potential energy. So on the right, you see a simple circuit, and we're going to talk more about circuits. Okay, we're going to go into more details of them soon. But this is just a battery connected to a light bulb. One terminal is the positive terminal, one is the negative terminal. There's some sort of flow of energy through this resistor, really. Remember, a light bulb is really a resistor. Okay, it slows down the flow of electricity. This is 19.3. That's all right. So what's happening here is this. There's a lot of potential energy, okay, from lead A to lead B. But then when it gets to lead B, all that energy is converted into what? What's converted to when it gets to the light bulb? Not kinetic energy. Heat or light energy, okay? Like you're looking at light. So you're going to see there's some sort of reaction going on here where light is being given off, and that potential energy that the charge carriers had gets dropped. Okay, that's from B to C, it drops. Then, from C to D on the way back, there's still no potential energy of the charge carriers. They have no potential energy. But then when it gets to D, what does it do? It refuels, right? So from D to A, take a look at what happens. The potential energy of the charge carriers do what? Jump back up to the level they started with. So it's just a cycle. Okay, it's a cyclic process. So the electrons are moving in this circuit. So think of it as the charge carriers having energy when it starts, when it comes out of the battery. It goes through the resistor. That energy is converted to some other form. It could be heat, it could be light, it could be something else. Okay? Then, after that, it could be mechanical energy, right, to turn a crankshaft. Now, after that, it goes back into the battery. The charge carriers gain more potential energy. Okay, so what we're going to do today, is talk about power. Okay, we're going to talk about power and how it's related to this. And you'll notice I made a little analogy here, and it's the analogy of gravitational potential energy. When an object falls from the sky, it starts with higher gravitational potential energy, and then it goes to lower gravitational energy. So it starts at high energy, it loses energy in this situation, similar to an object falling, and then if it were shot back up, it would be gaining the energy again.
I had a question in general. Why, when they record how much electricity you use, why do they measure it in watts instead of columns?
Let's hold off on your question for a sec, because we're going to talk about kilowatt hours. So just hold off for a little bit. It's going to come up at the end of the lesson. Okay? But we'll definitely talk about that. Good question. Very good. All right. So let's take a look now at our definition of electric power. Please remember, and you're not going to see it on the board, but just jot it down maybe on the side. If you remember the definition of power, power was the rate at which work was done. Remember, it was work over time, the rate at which work was done. But if you remember, work has units of joules. So we're just writing power as the change in potential energy, because that's also the work done. Okay, the work done on the charge carrier, or the change in its potential energy. The charge carrier is that electron, how much energy it's changing by. So that change in potential energy that we looked at in the last graph, remember how we said the charge carrier, look, energy starts up here. It goes through the filament, it loses its energy to light. It goes back to the battery, it gains the energy. So this delta PE, the rate at which it's changing, or the rate at which its energy is changing, is really what power is. Okay? So the rate at which the potential energy is changing. So delta PE over time, the rate. Now, I'm not going to go through the derivation, but I did jot it down for you, if you want to write it down. To go from here to here, there's a bunch of substitutions, but for the sake of time, because this lesson is somewhat lengthy, we're going to say it's on 708 and 709. It's in your text. There's a full derivation there. So if you want to see where it comes from, that's where it's going to. But what we're going to look at now, and who remembers, what does I stand for? From our last few sections, what did I stand for? Current. And what did V stand for? Voltage. Remember, it's capital V now. Velocity is lowercase v. All right. Now, at this point in time, by the way, what is P again? Just so we're all clear. Power. Okay. Remember what power was? Power was a joule per second. Power was a joule per second, which is known as a watt. So we're still in watts. So here's your power consumption now. In a minute, you're going to talk about kilowatt hours. And think about that while we're doing this, okay? What that means. So the units are watts here. The current is measured in, what is it? Amps or amperes, good. And voltage is in, the easiest one? Volts. That's why I said it's the easiest one. Okay? So those are the units we have in this problem. Now, consider the formula V equals IR, right? Our Ohm's law formula. V equals IR. Better, Jack? V equals I was talking to Jack. Can you see that better now? So if we consider the formula V equals IR, and we go ahead, focus Max, and we go ahead and take IR and plug it in for V up here, because that's what V equals, right? V is IR. So by substitution method, we can substitute IR in for this V up top. So this becomes P equals I. Instead of V, just put another IR there, because that's what V really is. Again, substitution method allows me to put IR in for V, yielding this formula here. Well, that's actually great, because you know what that gives me? A formula that says I squared R. So now I've got another formula for power. I don't need to use IV. Remember earlier, we had P equals IV at the top up here. Whoops. Let me just get R is resistance. Okay. We had P equals IV, but what if we're not given the current and the voltage? What if we're given the current and the resistance? Then instead of using P equals IV, we use P equals I squared R.
What is R?
Resistance. So the resistor. Okay, the ohms value, remember? Oh, okay. The value of ohms was R. The resistance. So remember the light bulb? Okay, has a certain amount of resistance, the stoppage of, or the resistance to flow of electrons, that's what it is. It's like friction in a tubing system, the resistance it feels. Now, there's one other way to write this formula. We can solve for I in this formula right here. Solve for I in this formula. Good. So now, take that I, okay, take that I and plug it back into the original, which you can barely see. The original is all the way up at the top. Whoops. The original is all the way up here at the top. P equals IV up here. Okay, take the definition of I as V over R, okay, and plug this in for this I right up here. Okay, plugging it up there for that I. So you have P equals, and then instead of I, you put V over R times V. Very good. So this is what I is. It was V over R, and then times another V there at the end. So we end up getting another formula for power as V squared over R. So in the end, how many formulas for power? We're going to have 3 of them. Well, we have the original one we started with, change in potential energy over time, for sure, absolutely. But then we have P equals IV. We have P equals V squared over R. I'm only saying them in that order because that's what you can see. And then the last one down here, P equals I squared R. I squared R. I'm going to write them all. Okay? Any of those are fine. And they will all result in the same units in the end. Okay? They'll all give you the same units. What are the units again? Power? Watts. Watts. Sasha.
Will all of these units be given? All of these equations?
I haven't decided yet. I have to think about that. I really would like to only give you one and have you come up with the one you need every time. As like a practice method.
Test is this Friday or next Friday?
Is it next Friday? Is that right?
19th.
Yeah.
Next week's gonna be
19th.
Yeah, we have like 2 weeks.
We have 3 tests.
No, but
We
next
can't have 3 tests.
No,
We can only have 2 tests.
Reschedule it.
When I put it up, there was no test. You can look at the date I put mine up there.
we have English and you on that Friday, English on that Monday.
I hope doesn't. If there's a third, let me know and I'll talk to that person or we'll figure it out. All right. Let's take a look at an example. Okay, let's take a look at an example. Not a tough example at all. Okay, not a tough example at all. It's a matter of thinking about which formula you're going to use here. Okay, think about which formula you're going to use. Write your givens. This is where your givens are really helpful. What's the first given? Good. Voltage is 120. Second given,
Watts.
which is what? Good, power. It says the TV dissipates 1150 watts of power, right? Of power. And if you didn't know that, you know that watts are power.
So you're looking for power.
Calculate the net resistance of the TV. Find R. So pick the formula you need to use to find R, please. You have three choices. You have P equals IV. It doesn't look like that's going to work. We don't have I. You have a next formula. P equals I squared R. Still doesn't work because there's an I. So, Olivier? Yeah, V squared over R. Use V squared over R for this one. Okay, solve for R analytically, please. So switch the R and the P.
I have a question about physics.
Yep.
General physics. How do you measure the force of wind?
The force of wood?
Wind.
Oh, wind. I'm like the force of wood. Like the strength
No,
of it.
not.
I'm like, you want to know?
It's getting really weird right now.
No, like the strength of a piece of wood is called tensile strength. It's measured actually.
Yeah.
Our measurements. I think you meant that.
Like wind.
I measured-
The force of wind. There's many ways you could. You could think
It's just one
about.
mass.
You could have like. Think about how buoyancy is measured. You put an object in like water, and as far as the thing moves up, it's the amount of pressure pushing up on it. So you can measure the amount of pressure the wind pushes with, and if you know the cross-sectional area, pressure equals force over area. So you take the pressure, multiply by the cross-section of the actual object, and you're able to find the force.
As long as we're off topic,
There's other ways to do it too, but that's just one.
since we're off topic, can we maybe schedule a day and later in spring that we go outside for class and we can do something related to
Sure,
cars or I
that'd be cool.
Yeah.
Maybe
have
go
some
over to
fresh
Central
air.
Park and do
It
something
really
there.
Smells like summer.
Is
though,
it?
I'm
Yeah,
not
it
gonna
smells
lie.
so nice out.
Yeah, we should.
It gives us like
Smells like.
Hopefully we'll be able to do that egg drop also, so we'll get outside that day as well.
We
That'd be
can do
another
it
day
this one I
outside.
was thinking about.
No,
we
the
can't do
sidewalks
street.
there, man.
Yes.
Junkyard's fine. We'll figure it out. I gotta talk to Miss Coops though. Remember that's on my schedule for this week. What do you get as an answer, guys?
12.52.
What did they say? I got it first.
What are the units of resistance?
I was about to ask that.
Oh, color. Oh,
Units over coulombs.
Ohms. There it is, Jeff. Ohms.
Oh yeah, the upside.
Okay.
Upside down.
The capital omega symbol. Any questions on this example? Are we good on this, right? This is a pretty easy topic, I thought. The next thing we're going to do is something that, you'll be able to relate to. How many people live in a house? How many people live in an apartment?
House.
House, raise your hand. Okay. If you live in a house, do you ever see your electric bill, or you know an electric bill has ratings on it, right? Your parents probably take care of it, obviously, but in your electric bill, okay, your electric power cost,
I live alone.
listen, the electric power cost is the amount of energy you use. Now, power, if you remember, is energy over time. So the electric company is not really measuring your power, they're measuring the amount of energy you use. So it's a bit of a misnomer, and that's what I wrote here. This can be counterintuitive, since some people call them power companies. They're not power companies, they provide power, but they bill you for energy. So they're really energy companies in my mind, right? Energy. Think about that, and it really will help us in this next explanation. Now, the unit of energy that power companies base their calculations on is called a kilowatt hour. A kilowatt hour. The amount of energy delivered in 1 hour at the constant rate of 1 kilowatt. So if they're providing you 1 kilowatt of power for an hour, a kilowatt hour is the amount of energy you're getting. We know energy as, what was the other unit? Coulombs. Yeah, coulombs. But they don't measure them in coulombs. So what we're going to do is we're going to use a conversion to joules to see what's happening here. Okay? Let's stay with me here for a sec. So, start with 1 kilowatt hour. Okay, 1 kilowatt hour. Now, what we're going to do is we're going to start multiplying this by conversion factors. God bless you. Let's convert the numerator to watts by getting rid of kilowatts. How many watts are in a kilowatt? 1,000. Remember, kilo means 1,000. You don't have to do this every time. I'm just showing you this first. After this, you'll see how you can do it on your own. Now, We want to convert, good, hours into minutes, then minutes into seconds.
Minutes on the bottom.
Wait, put an hour on the bottom.
Hour on the bottom, because hour's up top originally.
60. And then you're going to put 1 minute on the bottom. You get 60 seconds on top.
In the back, guys, stop. And 60 seconds up top.
Why are we going to seconds?
Because remember that what we'll get here is a watt times a second. And a watt times a second is actually a joule. And we'll show how that works. Okay? So when we multiply these, you'll get a value of 4, what is it? No, 3.6 times 10 to the 6.
Yeah.
And the units are watts times second. And take a look, watch. Kilowatt, kilowatt, hour, hour, minute, minute. What's left?
Seconds to watts.
Watts times seconds. Now, how do we know that a watt times a second is a joule? Well, let's go over that.
Just how we're doing.
Well, besides, I already told you. Okay? Watts, remember, guys, this is, listen,
Energy is always.
this is energy. This is energy. Remember, a kilowatt hour is energy. So what we're trying to do is get it back to energy, what we know, which is joules. And let me show you how it works. Remember, power equals work over time. Solve for energy in this problem, or solve for work. Work equals power times time. Stop talking. Stop talking. Work equals power times time. Work is measured in joules. Power is measured in watts. Time is measured in seconds. So it turns out that a joule is also just a watt times second. Okay, based on our formula for power, moving the t over here, we get power times time is just work. Work is in joules, so a joule is watt times second. Here's watt times second. That's really just the joule. So a kilowatt hour, one kilowatt hour is this many joules. Is this many joules of energy that you're getting. Okay? Which could also be measured in coulombs. Okay? Which could also be measured in coulomb energy, you know. Now, here's what you want to think about.
Paranoid now.
Here's what you want to think about.
Conspiracy.
Joules.
Oh, my W times S is joules, man.
Sorry, man.
Okay? So again, 1 kilowatt hour is really this many joules. You do not need to memorize that conversion. What we're going to do now is apply this to actual real life and like looking at kilowatt hours and your cost. Okay? So we're going to look at an example of that. And that's what you need to worry about. So let's think about this. If we look at our units first, the units of energy are in kilowatts hours. So if you want to find the cost of your energy bill for the month, you want to think about the amount of kilowatt hours and the charge per kilowatt hour. Your electric bill will always tell you how much you're getting charged per kilowatt hour. It's an energy rating. Okay? So if you want to find the cost for this month, you need to take the kilowatt hours of usage, okay, which is the energy, and you want to multiply that by the cost per energy, or the cost per kilowatt hour.
So the kilowatt hours cancel out.
Yes, leaving behind cost.
I feel like the flies are in the house.
There was a bird in Grand Central yesterday.
There's always birds. Always birds.
I know, but it almost hit me.
So that's the story.
Yeah.
Which is the story? There's a very
Breaking
good
news.
guy.
It's kinda funny.
It almost hit me.
I'm not trying to be mean, but that's kind of funny that you said there was a bird. You started with there was a bird in Central Park yesterday, right? Oh, Grand Central. I think you said Central Park. That's why I was laughing.
Central Park.
I'm sorry, Bob. I think you said Central Park.
Joey.
Is that why somebody else clapped because they heard Central Park also?
See a deer?
Tell me.
Central Park.
I thought I heard you say Central Park, and I said that. Boy, there's a lot of birds. That said, yeah, in Grand Central, really.
Yeah. It was like, I was like,
Have you ever got one on the train before? There's videos on the subway of birds getting caught on the train, on the subway train. It's kind of messed up. The bird starts going nuts because he can't get out. People don't know what to do. When people are doing this, it just excites the bird more.
No, I've seen where it walks in and it walks out as if it was like a.
Never seen that.
I'm trying to get statistics. That's really funny.
So,
It just walked out like a person.
what we have here, Garrett, sit down. Come on. Let's go. Stop. What we have here is this equation. If we want to find the cost of our energy bill, we take the amount of energy used in kilowatt hours and we multiply it by the cost per energy, the dollars per kilowatt hour, which is the cost the company gives you. So they're going to tell you something like, we're charging you 50 cents per kilowatt hour, and you used 20,000 kilowatt hours this month, so you're getting charged $10,000 for your electric bill. I mean, that's insane, right? You would never get charged that much. So what we're going to do is look at a real example. Okay? A what? Electric bill? It depends on how many people live there. Like a standard family in a house that has gas also, or the burner's electric? There's so many other questions. In the house that I lived in D.C. in the past, I think our energy bill was like $150 a month total. But that was because we were all like, none of us really used the air conditioner at all. Yeah, we're not in, like, I don't use an air conditioner ever. I don't like to use an air conditioner. I mean, and it also makes me sleep terribly. I don't like to sleep in the cold air.
I can only sleep in the thing.
Yeah.
I sleep in like.
A lot of people are like that. I know, a lot of people are like that.
Fan on in the winter going on.
Right, please, right as we talk.
Can I let it snow? I sleep outside in the snow.
It sucks.
No,
sleeping in the same-
no iPad mini today.
same
At
room as
least,
my
at least
brother.
you have a bed.
Max? You made eye contact? I started talking to you and you looked that way. No iPad mini today?
Yeah, no, it's,
Not today?
I kind of like drive.
Ah,
Yeah, but I have insurance on it. So I
okay.
should-
Nice. Good.
It's good to like.
All right, so we've all written this, right? Because we're talking, so we're all done writing it? Come on, guys, please write this. I know we're talking about other conversations, but you need to... Yeah, obviously, Jack, you're good. That's fine. So, you accidentally leave home without turning off the lights in your bedroom. Shh. Listen. There are 3 bulbs running on the ceiling light fixture. Stop talking. There are 3 bulbs running on the ceiling light fixture at a power level of 100 watts each. And you return home 10 hours later. It's like a standard light fixture. If your electrical energy costs 30 cents per kilowatt hour, what does it cost you while you're out? Okay? So Garrett, give me some piece of information. I'll show your hand. Oh, what's up, Garrett? Okay. So somebody give me a piece of information here. What do I have?
30 cents for 100 watts.
Okay, how many bulbs though? How many bulbs? 3, so how much power is being used, guys? Thank you. Come on, you need to focus. So there are 3 bulbs running at 100 watts each, so you're using 300 watts of power right now. How much time went by, guys? How much time went by?
1 hour.
10 hours.
10 hours. Okay? And remember, we want to use the equation cost equals kilowatt hours times cost per kilowatt hour. But we don't have kilowatt hour, but we have the watts. Convert that to kilowatts. What is that?
0.3 kilowatts.
Good, Molly. 0.3 kilowatts. So we have kilowatts and we have hours. So if we want to get, guys, you're focusing, I hope. If we want to get kilowatt hours, we need to multiply those 2 numbers, power times time. So the kilowatt hour rating is just going to be 3 kilowatt hours. Again, take your kilowatts, the amount of power that the light bulb draws over a 10-hour period, that'll give you the amount of kilowatt hours in energy. And how do you remember that? Power is really energy over time. Therefore, the amount of energy is the power times the time. So we took the power right here and multiplied it by the time right here to get the amount of energy, and that's the energy that goes in right here. Okay, that's the energy that goes in right there. Sash.
Orange, watts, joules times.
Watts are joules per second also.
So
Yep.
then why would it work with hours? Because then isn't it per second?
I'm just using what you get as a rating when you get your bill is in kilowatt hours. So I'm trying to show you guys that.
Isn't watt per second though? So wouldn't it be
A watt is a joule per second. We converted that a little while ago. Remember the conversion that we did? We got rid of our hours and went to seconds to get back to that. It works, trust me. Just take a look at it again. Maybe it'll help, okay? All right, let's fit. We have about 2 or 3 minutes here. It's 9:55.
So if you say something has
So-
100 watts, that means it's per hour?
Say again?
So if you say something has 100 watts, that means it's per hour?
No. The time was given in 10 hours. That's the only reason it's in hours. Watts or joules per second, absolutely. Okay? But we're given hours right here. Okay? So we can multiply the watts times the hours to get the kilowatt hour rating. Okay? Now, the cost per kilowatt hour is 30 cents per kilowatt hour. That's $0.3 per kilowatt hour. Yep. So what do you end up getting here? What do you end up getting for the cost? 0.3 times 3, how much does it cost you? 90 cents.
You have 3 minutes.
So if you think about this, okay, you leave your house with one light on for 10 hours, meaning like a normal day where you go to work for 10 hours probably during the day. One light on is $1 out of your pocket.
What?
Imagine that, one light fixture. Say you leave like 5 lights on, it's $5. Every day that adds up. You guys got to think about this stuff. It means a lot, right? Energy. Okay? Think about that for real. And I didn't realize that until I started living on my own and I started paying the electric bill. And I'm like, wow, this bill's crazy. So I was cognizant of it and I started realizing I'm not turning off enough lights in the house when I'm done with the room. You know? So I make sure that I shut the lights off. And this is real. Okay? Your homework, okay, is up on the board.